What's up, everybody? This is Mr. Richardson coming at you live through the power of the internet. And what we're going to be discussing today is how do we calculate the probability of single and compound events. This is the first video in my series about probability, so make sure you hit the subscribe button below so that you can get the updates on all of the videos in this series. Let's jump right into it. The probability of an event happening is the likelihood that that event occurs. When we do this, we write P open parentheses and the event within the parentheses. Maybe I want to know the probability that it's going to rain, the probability that the Knicks will win a basketball game. These are all different events that I want to know the likeliness that they happen. An outcome is the result of a single trial or a single experiment. That result could be the Knicks winning a game, or that could be the result of flipping a coin and it shows up as heads or tails. A sample space is all of the possible outcomes of an event. When we write the sample space, we use these brackets on the outside and we write all of the outcomes on the inside of the bracket. That outcome could be the first, the second, the third, all the way up to the nth outcome. A tree diagram is just a visual representation of a sample space that could look like this. It has line segments pointing out all of the different possible paths for the different outcomes. In this one, we can see we start here, and there's an outcome of a head and a tail for flipping a coin, and then again a head and a tail. When we do tree diagrams, we can use them to determine the probability of individual outcomes within the sample space by multiplying the probabilities that we get on the line segments. The way to calculate probability is to use the following formula. We want to calculate the number of wanted outcomes and divide that by the number of possible outcomes, remembering that the sample space shows us all of the possible outcomes. A few things to keep in mind here are that probabilities can be written as fractions, decimals, or percents. Typically, I like to talk in percents, but I like to write decimals. Fractions are always very useful as well, especially for numbers that don't easily convert to decimals. Another thing to keep in mind about probability is they always range from 0 to 1. This chart here really helps me think about different probabilities. For instance, if a probability is 0.5, or 50%, that means that an event is equally likely and unlikely to happen. Where if a probability is 1 or 100%, that event is certain it's absolutely going to happen. As we go from 0.5 to 1, the events get more likely to happen, and as we go from 0.5 to 0, the events get less likely to happen. For instance, an event that has a probability of 0 or 0% would be an impossible event, something that could never happen. Let's look at an example to bring all of these definitions together. In this example, I roll a six-sided die, known as a d6, and I roll that once. And what I want to know is first the probability of rolling a 5, then the probability of rolling an even number, and finally the probability of rolling an even number and a multiple of 3. Sometimes I'll start out by drawing a tree diagram that shows me all of the possibilities. Here I'm going to roll a die once, and the different possibilities, if it's a d6, which is a six-sided die, is the dice could result in a 1, a 2, a 3, a 4, a 5, or a 6. All of these probabilities are likely. They're all 1 out of 6. So our sample space here is all of the possible outcomes. In this case, the possible outcomes are 1, 2, 3, 4, 5, and 6. When I want to see the probability of rolling a 5, it's how many times that desired outcome of 5 happens over the total number of outcomes. Here I can see that there's 6 total outcomes, but only 1 5, so the probability of rolling a 5 is just 1 out of 6, because there's one scenario of a 5 and 6 possible scenarios. In part B, I want to know what's the probability of rolling an even number. Well, first I have to decide what are the wanted scenarios or the wanted outcomes, and in this case the wanted outcomes are an even number. Well, how many of the numbers in our sample space are even numbers? Here we can see those numbers are 2, 4, and 6. So when I go to calculate the probability of rolling an even number, it's the number of wanted outcomes. Here I can see we have 3 wanted outcomes over the total number of outcomes, which is 6, would be a probability of 3 over 6. When we calculate probabilities, we always want to reduce our fractions to simplest form, so 3 over 6 would simply reduce to 1/2. In part C, I want to know what's the probability of rolling an even number and a multiple of 3. Well, we already know all of the wanted outcomes. For even numbers, the possible even numbers are 2, 4, and 6. Now let's look at all of the multiples of 3. If I think about the multiples of 3 in our sample space, the only multiples of 3 are 3 and 6. Now, if I want something to be an even number and a multiple of 3, it needs to be in both of these two sets. The only number that appears in both of these two sets is the number 6, so there is one scenario that is an even number and a multiple of 3 out of 6 possible scenarios, meaning the probability of rolling an even number and a multiple of 3 is 1 out of 6. Let's see if you could try an example on your own. In this example, there's a spinner with 14 equal areas numbered 1 through 14. If the spinner is spun one time, what is the probability that the result is a multiple of 6 and a multiple of 4? First thing I'm going to do to answer this question is to write out the sample space. The sample space is the numbers 1 through 14 that correspond to the 14 different spaces of the spinner. Now I want to write out all the numbers in our sample space that are multiples of 4. In that case, it's only 4, 8, and 12. Those are the only multiples of 4 in our sample space. Now I want to similarly look at the multiples of 6. The only multiples of 6 in our sample space are 6 and 12. Finally, I want to see how many are multiples of 4 and 6. If I look at where these overlap, the only numbers in this sample space that are multiples of 4 and 6 would be 12. When I go to calculate this probability, remember that probability is the number of wanted outcomes over the total number of outcomes. I can see that there's 14 possible outcomes, and of those 14 possible outcomes, the only outcomes that are multiples of 6 and 4 is this number 12, so one scenario out of 14. Let's try another example. This problem is very similar to the last one. Here we have a spinner with 13 equal areas numbered 1 through 13, and if the spinner is spun one time, what's the probability that the result is a multiple of 3 or a multiple of 2? First thing I'll do to answer this question is to write out the sample space. The sample space is the set of all possible outcomes. For this scenario, it's the numbers 1 through 13 that represent all of the spots on the spinner. Next, let's write out all the multiples of 3 in our sample space. The multiples of 3 in our sample space are 3, 6, 9, and 12. Next, let's write out the multiples of 2 in our sample space. Those are the numbers 2, 4, 6, 8, 10, and 12. For this question, we want to find the multiples of 2 or the multiples of 3 in our sample space, which mean it could be a number on either list. When we write this out, the multiples of 2 or 3 in our sample space would be 2, 3, 4, 6, 8, 9, 10, and 12. It's all of the numbers that appear in these two spaces without showing any repetition. If I want to find the probability that I have a multiple of 2 or a multiple of 3, it's the number of wanted outcomes, which is 1, 2, 3, 4, 5, 6, 7, 8 outcomes out of 13. Let's go and define compound probability for our notes. Everything that we've done so far is a single event. What a single event is when an event has only one possible outcome. In all of the scenarios that we've done so far, there's only been one possible outcome, regardless of how complicated that outcome might be. A compound event is different in where a compound event has more than one possible outcome. Typically, there's 2, 3, or even 4 possible outcomes. Those outcomes we list with a comma. The way I would read this is what's the probability that event A occurs, then event B occurs. The order here is important. In order to calculate this, you just multiply the two probabilities together. If we had a tree diagram, we could multiply all the probabilities along the path that represent the outcome we want on the tree diagram. Let's look at an example of this. In this example here, I roll a 6-sided die and then I flip a coin. Part A says, what is the probability of rolling a 5, then getting tails? And part B says, what is the probability of rolling an even number and then getting heads? Sometimes I'll start with a tree diagram to help me jump into the question. If I look at the tree diagram, it starts like this, with the numbers 1, 2, 3, 4, 5, and 6 from rolling that 6-sided die. We know that the probability of each of these events happening is 1 out of 6. After I've rolled that die, I then flip a coin, and each of these branches then have another piece of the tree diagram to them that looks like this. What this means here is that I could roll a 2 on the dice, and then I would get a head on the coin. Meaning the probability of rolling the 2 would be 1/6, and the probability of getting a head on the coin would be that 1/2. Similarly, this leg of the tree diagram means that I roll a 4, which happens 1/6 of the time, and then I'd get a head on the coin, which would happen 1/2 of the time. The sample space here is a little bit more complicated. Remember, the sample space is all of the possible outcomes. Here, the sample space is listed here. We can see that there's 12 possible outcomes. You could get the number 1 and then a head, 1 and then a tail, 2 and heads, 2 and tails, and so forth. So that represents the sample space. In part A, I want to know what's the probability of rolling a 5 and then getting tails. Well, because this is 2 events, we can just multiply the probability of each. I know the probability of rolling a 5 is 1 out of 6, and the probability of getting tails is 1/2. So if I want to find the probability of rolling a 5 and getting tails, I just multiply these 2 events, and I can see that the probability is 1 out of 12. Looking at the tree diagram, that represents this branch. You rolled a 5, and then you got a tails, so I just multiplied 1/6 times 1/2. In part B, we want to know what's the probability of rolling an even number on a die and then getting heads on a coin. Well, if we look at our tree diagram, we could see that there's 3 ways to get an even number. We could get 2, 4, or 6, and all of these have a probability of 1/6. Then each of them want to get a tails, which has a probability of 1/2. So for each of these, it's 1/6 times 1/2. And when I do 1/6 times 1/2, I get 1/12, and there's 3 of these, which is 3/12. Well, we could also just do this using the formula, knowing that the probability of rolling an even number is 3 scenarios out of 6, and the probability of rolling tails is just 1 out of 2. 3/6 times 1 out of 2, multiplying across, 3 times 1 is 3, 6 times 2 is 12, I get 3/12, and of course I should simplify all fractions. Here I'd get 1/4 as a final answer, meaning the compound probability of rolling an even number and then getting heads is 1 out of 4. Let's try an example on our own. In this question here, I want to spin the spinner below and then flip a coin. Find the probability of getting the spinner to land on a green region and then getting tails on the coin. I can see that this is a compound probability because there's one event happening after the other. First thing I can do is bring up our compound probability formula and plug in the 2 events I have. In this case, I have the probability of spinning this spinner and it lands on a green region, followed by then a coin landing on tails, which would be the probability of the green regions multiplied by the probability of tails. Now all I want to do is plug in these 2 probabilities and multiply. Well, the probability of this landing in a green region is 1 region out of 3, and the probability of a coin landing on tails we know is 1/2. When I multiply across here, 1 times 1 is 1, and 3 times 2 is 6, making the probability that spinning this spinner and it lands on a green region, followed by flipping a coin that lands on tails, is 1 out of 6. Let's try another example. This question reads as follows. Mr. Richardson rolls a 6-sided die, then flips a coin, and then spins the spinner shown below. What is the probability that Mr. Richardson obtains an even number on the die, then gets heads on the coin, and then gets a multiple of 5 on the spinner? I can see this problem will require a compound probability formula because there's multiple events happening, and we can extend our probability formula to work for 3 events as shown. Here the first event is getting an even number on the die, getting heads on the coin, and a multiple of 5 on the spinner. If we go to get an even number on a die, we know the probability of that happening is how many favorable outcomes out of the total number of outcomes. Well, on a coin, there's going to be 6 possible outcomes, and there's a 2, a 4, and a 6, which is an even number, so that probability is going to be 3 out of 6. Now I need to multiply that by the probability of a coin landing on heads. We know that probability is 1/2. And finally, I want to see what is the probability of getting a multiple of 5 on this spinner. Well, the only multiples of 5 on this spinner are the number 5, the number 10, and the number 15, which is a probability of 3 over 15. Now we simply multiply across. 3 times 1 is 3, 3 times 3 is 9. 6 times 2 is 12, 12 times 15 is 180. Now we just want to simplify this. These both have common factors of 9, so we can divide them each by 9, and the probability of this happening is 1 out of 20. Let's try another example. This question reads, suppose you choose a marble from a bag containing 5 red marbles, 5 blue marbles, and 2 green marbles. You don't return the first marble to the bag and then choose again. Find the probability of picking a blue marble followed by picking a green marble. This question is a little bit different than the ones that we've done before because we don't return the first marble to the bag. So when we do these compound probabilities, the probabilities are changing as we take a marble out of a bag. To demonstrate this, I'm going to show this diagram here, which shows the different types of marbles that are in the bag. We can see that we have 5 red marbles, 5 blue marbles, and 2 green marbles. Here what we want to do is find the probability of taking a blue marble followed by taking a green marble. Well, when I go to take a blue marble, I can see that there's 5 of them out of 12, so the probability of taking a blue marble out of the bag is 5 out of 12. But then what happens is kind of interesting. I've now taken any one of these 5 blue marbles out of the bag. Let's imagine I've taken this one out. Now when I go to take a green marble, the probabilities have changed. Sure, there's 2 green marbles, but there's only 11 marbles left in the bag, so the probability of taking a green marble in this scenario is 2 out of 11. Now we multiply across. 5 times 2 is 10, 12 times 11 is 132, and when I simplify this, I can see that the probability of taking a blue marble out of the bag followed by a green marble out of the bag is 5 out of 66. Let's see if you can try an example. In this example here, a cooler contains 12 drinks, 5 lime drinks, 3 apple drinks, and 2 grape drinks. Abby is the first in line for drinks, Telly is second. What is the probability that Allie will get a grape drink and Telly will get a lime drink if they are given drinks at random? In order to answer a question like this, I find that it helps to draw a diagram. Here I've drawn a diagram with the different drinks in the cooler. We can see that we have 2 grape drinks, 5 lime drinks, and 3 apple drinks. Here we want to find the probability that Abby gets a grape drink followed by Telly getting a lime drink. So first I want to find the probability of getting a grape drink. I can see that this probability is 2 out of 10. Now once Abby has gotten the grape drink, there's a drink that's been removed from the cooler. It doesn't matter whether it's this one or this one as long as we take a grape drink out. Now Telly is going to get a lime drink. When we go to get a lime drink now, there's still 5 lime drinks available, but there's only 9 drinks left, so the probability of getting that lime drink, given that we already took a grape drink out, is 5 out of 9. To calculate this probability, simply multiply across. 2 times 5 is 10, 10 times 9 is 90, and when I simplify 10 divided by 90, I can divide the numerator and denominator both by 10, and I'll just get 1/9. Let's try one final question. Suppose we choose a marble from a bag containing 3 red marbles, 5 blue marbles, and 2 green marbles. You don't return the first marble to the bag and then choose again. Find the probability of choosing a red marble followed by another red marble. With these questions here, I'll always start by drawing a diagram, and here I have a compound probability of taking a red marble followed by a red marble. When I go to take the first red marble out of the bag, the probability is 3 out of 10 because I can see that there's 3 red marbles out of 10 possibilities. Well, regardless of which red marble I've taken from the bag, the number in the bag has changed. Not only the total number of marbles, but also the number of red marbles in this scenario. When I go to take this next red marble out of the bag, there's not 3 red marbles anymore. I can see that there's only 2 red marbles left for a total of 9 marbles. When we multiply across, 3 times 2 is 6, and 10 times 9 is 90, and then we just simplify the fraction 6 over 90 to get 1 over 15. Well, that's it for this video, and that's it for me. I hope in this video you learned a lot about probability. I hope you learned how to calculate probability for single events as well as compound events. Until next time.